Okay. Okay, good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheP at the moment. This afternoon, it is my big pleasure to introduce to you one of our own, Professor Michael Kastner, who is the chief researcher of NITheP at the University of Stellenbosch, and he's also professor at the University of Stellenbosch as well. Yeah, and Michael studied in Germany. He did his PhD at the university at the Friedrich Alexander University in Erlangen, and he joined NITheP in 2009, so more than 10 years ago. And since then, he's been a very productive researcher and produced lots of very interesting and nice papers. And that's the reason why he's here this evening, yeah, to share with you some of his recent results. Michael, we are very happy to have you here this evening and that you agreed to share with us some of your wisdom. And if you would like to start sharing your screen, you can start your presentation. And I always forget to say, please, if you have questions, make use of the question and answer facility at the bottom of the screen. And since we are not so many, we might even have the time to ask people to pose their questions in person at the end. And Ilya, Dr. Sinaisky, who you see at the top, he will coordinate the question and answer sessions after the talk. So Michael, if you would like to share your screen, you're most than welcome to start. Thank you very much.
Okay. Thank you, Francesco, for the kind introduction. Can you all see my screen, my slides?
Yes, it's perfect. Thank you very much.
Yeah. So it's my great pleasure to have the opportunity to tell you a bit about my research interest, the research that is being done in, or has been done in my group over the past years. And for this talk today, I chose as a topic, as you can read, equilibration timescales of isolated quantum systems. And the topic is, well, I would say the talk is based on a paper indicated at the very bottom of my slide. The first author is Daniel Nicholson, who was a postdoc at the time working with me. And most of the credit for the work reported here goes to Daniel. And while I write here, the talk is based on that paper. It is also true that much of the talk will not be directly about the content of that paper, but I will spend at least 2/3 of the talk to provide a much more general introduction to a topic that has become very timely in the past decade or so, and which I find very interesting, and that this is the question of equilibration in quantum systems more generally, and I'll talk about the timescales only at the very end of that talk. So let me tell you what the talk is about. What I have in mind mainly is a very basic and also very fundamental question of physics, the approach to equilibrium. So think of the simple sketch that you hear on that you see on that slide. I have two macroscopic pieces of matter at different temperatures, T1, T2. If I join the two so that they are in thermal contact with each other, then the expectation is that they will approach equilibrium, some equilibrium state, and more generally that this state will be a thermal equilibrium state. And the setting here that I have in mind of a large but isolated system, so these two systems, and then later they are in contact with each other, but there is no bath or so surrounding them. This context of isolated quantum systems is very much at the heart of thermodynamics, the old theory of thermodynamics, where you construct heat engines, for example, by putting one piece of matter in contact with another. And so this is a question that has interested people from when thermodynamics was invented, and then later on also when statistical mechanics more than a century ago came into being. And so the question I have in mind is in some cases even explicitly given as an axiom of thermodynamics. So systems in contact with each other approach equilibrium. And sometimes it's more indirectly implied in the theory of thermodynamics, but it is a very basic ingredient of thermodynamics. So there is this very foundational aspect of the question I'm interested in, but then also it has become a much more applied question more recently. There has been massive progress in experimental physics, where experiments with isolated many-body quantum systems have become possible over the past 10, 15 years. And there's many experiments with cold atoms now being conducted where isolation from the environment can be achieved with to a very high degree. And I've shown here a plot which I don't want to discuss the details of what is shown here, but there is a time axis going down. There's two blobs initially, which are essentially two Bose-Einstein condensates, like consisting each of thousands of particles. And they are in something like a parabolic potential. So they start moving towards each other and they should meet each other. And well, the initial expectation of the experimentalist was that there was lots of collisions happening and that the system should thermalize quickly. But the finding was that on the timescales accessible in the experiment, no thermalization was visible. And there was questions of that kind that led people to a renewed interest also in the questions, when do we see thermalization, when does it not happen, or not on the timescales that we can access in physics and so on. So there is this very applied side to this question as well. I was starting my interest in this field started from a more applied side, but today I will mostly talk about the fundamental question, like for the questions of thermodynamics, what is the status of this thermalization or equilibration in quantum? And the direction I want to take is I would like to use a microscopic theory, like quantum mechanics, based simply on the Schrödinger equation, to derive or justify or argue in favor of why we see equilibration, under what conditions do we see it, and what are maybe other conditions that can prevent thermalization to happen. So this is the kind of questions I want to ask. I want to go in the spirit of statistical mechanics, but maybe sometimes by different methods, from a microscopic description, the theory that we have based on Schrödinger's equation, and answer or understand macroscopic behavior that we expect to happen or know to happen or want to justify. In a course on statistical physics and thermodynamics, in many cases, there's very little said about why statistical mechanics, for example, and thermodynamics work, or this microscopic justification is sometimes not given at all, or not on a very deep level. But there's one notion that is frequently mentioned, and this is ergodicity. So this goes back to Ludwig Boltzmann, who came up with the ergodic hypothesis in the early days of statistical mechanics. At that time, it was classical statistical mechanics. So only on this slide, I'll not talk about quantum systems, but about classical many-body systems. And the core of this ergodic hypothesis is, in words, time average equals ensemble average. So the ensemble average is the microcanonical or the canonical ensemble, and the time average is, according to Boltzmann, what we might be interested in as a quantity that describes equilibrium. And as a formula, you see down here that the microcanonical average of some function should be equal to the long time average. If that is the case, and the long time average qualifies as equilibrium, then we have a reason why we can use the microcanonical ensemble as a calculational tool to learn something about the equilibrium state of a system. And I've illustrated this concept of ergodicity here in a very simple sketch. So this square that you see here, think of that as the energy shell. So this is in classical phase space, many particle phase space. This is the manifold of states that correspond to a certain value of the energy with respect to some Hamiltonian function or a small interval of that energy. And then ergodicity tells us if the dynamics is such that from a given initial state, or maybe from any initial state, a trajectory in time of the system in phase space will cover that phase space homogeneously, then if this is what happens, then this statement here will be true, the ergodic hypothesis will be true, and then we find the equilibrium values in the long time limit that are predicted by the microcanonical ensemble. Now, this is an old idea, and it was very fruitful in some sense. In mathematics, there's a whole, essentially a field of mathematics, ergodic theory, that developed out of this physics questions. But for physics, I would say it wasn't so successful in the end. And there are different aspects to it. And I think it's really an interesting point here to make. So for one, people have tried to prove ergodicity of physically interesting systems for a very long time and with lots of effort. And there is a single system that I would say qualifies as kind of related to physics. It's called the Sinai billiard. It's two disks in a square that bounce around. And I think this is the only kind of physical system for which it was possible to prove ergodicity. All the rest is really super abstract toy models where you can't see a connection to physics. So it's not a very practical tool, ergodicity, but it could even worse. Like in the 1970s, two people, Meyer and Marcus, they published a paper in which they proved, a mathematics paper, in which they proved that generic Hamiltonian systems are not ergodic. So only very, very special systems have a chance of being ergodic, and all the others aren't. So generically, ergodicity is not realized in physics. It just doesn't play a role. So lots of problems here. And the third problem I want to mention is that ergodicity refers to this long time average. But this is not what we measure in physics. People find equilibrium by measuring instantaneously or over a very short interval of time. You don't take very long time averages to see thermalization. You just measure at some late time, and this is where you find it. So this is not even the right object. So you see lots of problems that come with the idea, and in this, so I would qualify the idea of ergodicity as unrealistic in several ways. And in this paper that I cite here, hidden in some philosophics journal, the authors Ehrman and Redey, they argue quite nicely that the idea of ergodicity is both too weak and too strong in some way. Too weak in the sense that a long time average is not strong enough to justify why we see thermalization or equilibration in nature, and too strong that too much is demanded by asking for this equation here, too much so that essentially no physical system can satisfy it. So as you have heard, I'm not really in favor of this idea, and I want to suggest to replace it with another idea, and it's the idea of typicality. This is also not new in some sense, but the idea was around for 90 years already and then got revived about 10 years ago. And together with tools from quantum information theory and others, it was a very fruitful revival that led to many new and interesting results over the past 1.5 decades or so. So what is this typicality? In a nutshell, typicality says almost everything is equilibrium. So if we compare this to ergodicity, where we needed a very special dynamics to cover this energy shell homogeneously to arrive at a justification maybe of statistical mechanics. Here, the idea is the following. If these are the states on the energy shell, and if everything essentially here is equilibrium, and only a tiny corner of that energy shell corresponds to non-equilibrium states, then if that is the case, equilibration occurs in a much more natural way. So imagine for some, by some mechanism, you draw by random one state from this energy shell. With very high probability, it will be an equilibrium state because almost all of them are equilibrium. If you think in the dynamical context, if your system is maybe prepared in one of those rare non-equilibrium states down here in the corner, and if the dynamics is not too special, then you can expect that the dynamics will take the system from non-equilibrium into equilibrium and remain there for a long time. So the moment we have this picture of equilibrium is typical, we don't even need such a special dynamics anymore, but we only have to exclude some very, very special dynamics which maybe make us move around only in non-equilibrium and never equilibrate. But this would be a rare thing, an exceptional dynamics, very unlike the ergodicity scenario where we needed a very special dynamics to have thermalization. Now that thermalization is so ubiquitous in nature, it sounds very compelling to have a mechanism that happens typically because equilibrium is so typical. To make this scenario work of typicality, we will have to think what a suitable notion of equilibrium is. And I'll come to that. I'll have a slide with definitions of equilibration. So the idea will be a bit, we define equilibrium in a way that it is easier for a system to call it an equilibrium, but it will be physically very realistic. And once we have this, almost everything is equilibrium. And then we can not only do we have this nice picture how things work, but we also will have mathematical methods to prove that equilibration happens in a probabilistic sense. And this is where I will be going in this talk. So to make this typicality work, we have to adjust the notion of equilibrium. So now to understand how we have to adjust it, I want to first introduce the setting that I'll be considering in this talk. So I'll talk about equilibration in isolated quantum systems. I want to keep things simple, so I will not do the most general scenario, but I'll do something that we can work with a little bit more easily. There's many generalizations that can be done. So there's a Hamiltonian operator, and I've written it here in the energy representation. So these n's, kets and bras, are energy eigenstates. The En are the energy eigenvalues. The sum goes from n1 to d, where d is the dimension of the Hilbert space, which I assume to be in general large but finite, and then automatically we also have a discrete spectrum. To keep the notation simple, I'll assume that these En are not degenerate, but this is not necessary for anything that I'll be telling you. It only makes the notation simpler and is more convenient to work with. So we can have degeneracies, it's not a problem. And the first important point that I want to make here, that with such a unitary dynamics driven by this Hamiltonian here, there will be no equilibration in the sense of a density operator rho, time evolved, will converge in the long time limit to some equilibrium state. This cannot happen. To make this clear why this is the case, let's look at this at a simple example that essentially implies this conclusion here. So what I do here, I look at the expectation value, the time evolved expectation value of some observable O, which is given as the trace over rho t times O. And then by the standard trick of quantum mechanics, inserting resolutions of identity, I can write this in this way. So these are sums over the energy eigenbasis, matrix elements of the initial density operator, matrix elements of the observable that I'm considering. and then these phase factors here, where the frequencies are given by differences in the eigenvalues. Now, what is the structure of this object? It's a sum over amplitudes times complex phase factors. Now, this is such a simple structure that one can essentially read off some properties of the dynamics that this object will have, but one can also formally prove what I'm saying now. So the dynamics of this thing here will be quasi-periodic. So we'll have something in the spirit of Poincare recurrence theorem. If we start somewhere in some state, then we will at some later time get arbitrarily close to that initial state. And this may happen at very, very late times, but this will happen eventually. And overall, the motion will be a quasi-periodic motion. And I have here a plot that shows what essentially will be happening here. What is plotted here is, as a function of time, I show the time-evolved expectation value minus the equilibrium value. I haven't defined this properly, but I mean, from the behavior here, you can guess why I call it the equilibrium value. I give a more precise definition in a bit. We may have started somewhere out of equilibrium, then on some time scale, the system is expected to reach this equilibrium value approximately, maybe cross that value sometimes, and it will have tiny fluctuations around equilibrium. But at certain times, usually much rarer than I show them here, there will be these spikes where larger deviations from equilibrium occur. Typically, the larger the system is, the rarer these excursions will be, and really large excursions will be very, very rare. So this is the kind of behavior that, based on this formula, we expect or even can prove that this is what happens. Quasi-periodic behavior, small fluctuations all the time, and very rare large fluctuations. So what can we deduce from this? What is the consequence of this? So the first one, this I find a very interesting one, and maybe you say it's obvious and yeah, we knew all along, but I found it interesting to realize this at some point really, that this equilibrium state here is not physical reality, but it is really a crutch. So nowhere here in time is the system usually not even close in some distance measure on operator space, not even necessarily close to equilibrium value. But for the chosen observable, expectation values will still be very close. So this equilibrium state is really a crutch that helps us to calculate the equilibrium value, but this doesn't mean that the system is in that state. It's only a useful calculational tool. And this I find very, very compelling and interesting observation. Second observation is a rephrasing from of the quasi-periodicity. Equilibration happens not for all times, but we can hope or expect or try to prove that it happens for most times. There will be times where the system is out of equilibrium, but they will be rare. So equilibration, we shouldn't even try to prove it for all times. It's not, in our setting, not the right thing to do. And a third observation, not all observables equilibrate. So it will not even be a good idea to try to prove, even in this, even allowing for fluctuations, it will not even be a good idea to try to prove it for the density operator, because I can always construct observables, which are self-adjoint operators as they should in quantum theory, that do not equilibrate. And the examples are simple. I mean, take this projector here on some energy eigenstate. This is an observable, it's a self-adjoint operator, and it is conserved under the time evolution. So if it's not in its equilibrium value initially, it will never go there. So we cannot expect this thing to do anything interesting. So we shouldn't look at the density operators. We shouldn't look at all observables, but we have to focus on observables that we declare as interesting. And these 3 points will be our guiding principles for defining equilibration in a good, suitable sense, and also to try to prove statements about equilibration. So now I get to the definition of equilibration, motivated by what I have just shown you. So as I said on the previous slide, we have to restrict the observables to a class of observables that we declare as the ones that we find interesting. And this means, for example, the observables that realistically can be measured in an experiment, because I mean, we want a theory that describes physics and not a theory that describes all operators that exist in the world if they haven't anything to do with physics or with the physics we want to describe in this setting here now. So I take observables from some set, and this set may consist of only one observable, but I can have several. It will not change anything about the definitions that I show here. So equilibration on the level of observables, first attempt, strong equilibration. So you already have seen that it will not work in our setting because of quasi-periodicity, but the first try might be just to say, well, I want the expectation value to converge to its equilibrium value in the long time limit. So it would look something like this: as a function of time, the OT minus O equilibrium does some fluctuations and converges. Quasi-periodicity forbids this. So in our setting, this is not the right type of definition. Let's try to do something that works for isolated systems and think of probabilistic equilibration on the level of expectation values. So I would ask that the time-evolved expectation value of O is very close to the equilibrium for most t, but not for all t. And here, this is the same plot that I had shown before. So something that wiggles around the equilibrium value for most times with tiny wiggles, but occasionally there will be larger excursions away. And these vague statements that I have here, so this wiggly equal and most, one can make precise in an epsilon delta sense. This is done here. So I would require to call a system equilibrated that the probability that for times either all reals or all positive reals, that the time-evolved expectation value differs from the equilibrium value by more than a value epsilon, that the probability of that to occur is smaller than some value delta. In this plot here, you can think of this in the following way. So around the value 0, you draw a small corridor, like a small area around that axis, and you call it in equilibrium whenever the expectation value is in that little corridor, and whenever you have an excursion outside the corridor, you call it non-equilibrium. So this epsilon here, this is the size of the corridor, and these delta, this is the frequency, or how often does it happen that such a ray excursion takes place. And this is a definition of equilibrium that works for these isolated systems and is in agreement with this behavior of observables in isolated quantum systems that I've shown you before. It's maybe not always, it's a good thing to work with. It's maybe not always perfect, and I'll tell you when it's maybe not sufficient and one would want to ask more and have a more strict definition and this is the following. You can have a system that, according to this definition here, is in equilibrium. So the expectation value is very close to 0. But this doesn't make predictions for measurement values. You might have a system where the expectation value is 0, but whenever you do a measurement on your system, you find that, say, the magnetization of the model you're looking at is not close to 0, but is like 1,000 plus or minus 1,000, but both of them as measurement outcomes happen with probability roughly 1/2, and this is why the expectation value is 0. So with this definition, you can have the situation that the expectation value is nicely in equilibrium, but whenever you measure your system, you will not find anything close to equilibrium. And again, this is not what we usually have in mind for a physics system. When we say, oh, my cup of coffee is in equilibrium, like the milk and the coffee have equilibrated, they're all mixed up, then it's not that I have the milk on the right-hand side and the coffee on the left or the other way around, but they're really mixed up. It's not that I find plus 100, minus 100, but I find 0. Last definition that I want to give is the one that, well, I have to say is my favorite one. I think this is a very, very nice way of putting what equilibration for, at least on a macroscopic level, is supposed to mean. And I call it probabilistic subspace equilibration. So what was the spirit here? What we didn't like here was that it didn't make, this definition number 2 didn't make predictions for measurement outcomes. So this we want to cure by asking the state of the system to be in that subspace of the Hilbert space that, when measured, really gives the desired measurement value close to equilibrium. How do we do this? We define an equilibrium subspace of Hilbert space. So of all Hilbert space, we take a part of it, and I'll argue later that it will be a large part of it. We take the part where, with respect to some observable O that I've chosen, I take all the eigenvalues, all those observable eigenstates, so eigenstates of the observable that I'm interested in. I take all those eigenstates, and of those, I pick all those eigenstates whose eigenvalues do not differ from equilibrium by more than delta O. So I take the eigenbasis of the observable, all eigenstates with good eigenvalues that I see as close to equilibrium, and these eigenvectors, they span a subspace of Hilbert space. And whenever my state now is mostly in that subspace, I call my system in equilibrium. Mostly in that subspace means I take my state rho t, the time evolved density operator, I multiply it by the projector onto that subspace. And whenever the expectation value of that projector, so the trace of that object here, is very close to 1, then my state is almost entirely in the equilibrium subspace. And when I measure the corresponding state, it will, with very, very high probability, give a measurement value that is very close to the equilibrium as indicated here by these dots. So this is a definition of equilibrium for isolated quantum systems that really, in my opinion, captures the core idea of what we expect that equilibrium means. We can measure at any late time instance, and with very high probability, we find a measurement value that is very close to the equilibrium value. Okay, this is a notion I'll come back to later. Before I do this, when defining equilibration, I may have said it before, want to state again that I use the word equilibration distinct from thermalisation, and one is a subset of the others. So equilibration means the system approaches equilibrium in the sense specified here on that slide. And thermalisation means that the corresponding equilibrium values are the thermal values as given by the microcanonical ensemble or the canonical ensemble, depending on the conditions. Now, here in my case, it will be the equilibrium values are the microcanonical values. That is thermalisation. The equilibrium value are something else. This is equilibration. Okay, now I think we are set up to look at what one can do with this notion. And so with a good notion of equilibration now at hand, I want to come back to the idea of typicality that I was mentioning before. And now where I had the classical picture before of that here, of the square here being phase space, now you can think of this as being the equilibrium subspace of Hilbert space. and that the non-equilibrium part of Hilbert space is just a tiny, tiny corner of overall Hilbert space. So in numbers, typicality means that the dimension of the equilibrium subspace is, well, smaller, but only slightly smaller than the dimension of the overall Hilbert space. If I have this situation, most states will be equilibrium states. And what is acceptable as slightly smaller, I mean, this can be made precise. Usually one wants that both parts of the Hilbert space grow with the system size in the same way, like grow exponentially with system size, but with different prefactors in the exponent. And this is what is enough and gives a good notion of typicality here. So what do we have now? What can we do with this idea? So we have something very concrete here that we can try to prove for well-chosen observables, but physically interesting ones, that the corresponding dimension of the Hilbert space is just a little bit smaller than the overall dimension, so that almost everything is equilibrium, and then we can do prove that a system equilibrates and so on with that. First consequence, if we have this realized a randomly drawn state from the Hilbert space represents equilibrium with respect to the observable O with very high probability. And the second, in principle, I've said this before, no special dynamics is needed to approach equilibrium and to stay there for most times. If almost everything is equilibrium and we start in that little corner here in non-equilibrium, if our dynamics is not very special in preventing this, we will move to equilibrium and stay there just because it's so likely and so big. The first statement here, that a randomly drawn state represents equilibrium, this was proposed and used as a new numerical method. So if your task is, you want to calculate numerically an equilibrium value of a many-body quantum system, that is a difficult task, and very often it's done by quantum Monte Carlo methods, and where the many different states are calculated with according, by Monte Carlo sampling with according weight factors. And this can be avoided with a good algorithm to draw a random state with a given energy or other constraints from Hilbert space. And so there is a way to use typicality for calculating equilibrium expectation values of observables. And the second property here about the dynamics and the approach to equilibrium, this has also been used, the spirit of typicality, to prove theorems about equilibration in isolated quantum systems. So this is what I have on this slide. And I mean, this is an introductory talk where I want to just give you a little bit exposure to a field. So I'm not trying to show in detail what exactly these theorems look like. I think that's just not the point here, but I want to give you an idea how such results look like and what they tell us. First, what is it that we want to achieve? The idea here is not to pick a special system, like pick your favorite model, the Ising model, a Hubbard model, or whatever, and prove that this system equilibrates or it doesn't equilibrate. But we would like to make statements about broad classes of systems and make statements what they typically do, and broad classes of initial states and of observables. And this is the spirit of what I'm showing here. There's a number of such results that have been established in various complementary settings, and this mostly means that the choice of the observable here, which I haven't yet specified so far, that different choices of observables can give rise to different kinds of results. So we look at equilibration on the observable level, and we have to decide on a class of observables which we declare to be interesting, and then we can show something. One choice is for macroscopic observables. I don't want to go into how exactly these are defined here, but they are those that for a large system in a macroscopic apparatus are the ones that we believe can be measured. And there's some results here. Subsystem equilibration, if you have a large system and you look at only a small subsystem of it, then this is a class of observables where one can make interesting statements. And then there's a third class, what I call physically realistic observables and initial states. That is mostly just saying that all observables we can deal with have a certain experimental resolution. We can't look any better, and you can translate this into conditions on the observables. And all initial states can be prepared only with a certain degree of accuracy, and this translates into a class of initial states. And for those classes, one can again prove equilibration in a mathematically strict sense. What is interesting here, I think, is the timeline of the results I've shown here, and I think it reflects the timeline of the field rather accurately. There's this one early paper from 1929 by John von Neumann. Then there's nothing for 80 years, and then in the early 2000s, people started again looking at this topic from this typicality point of view, and with new tools that had been developed in the meantime, making substantial progress subsequently. So statements or mathematical proofs of equilibration, how do such results look like? So here I have one for you, which I'll walk you through this equation, just for you to get an idea how this looks like. So this is a result taken from one of Goldstein's paper here. So this is one that refers to macroscopic observables. The object on the left-hand side here, this is essentially the probability of finding the system in equilibrium with the definition of the non-equilibrium of equilibration in this subspace sense that I've shown before. So of all times in the interval between 0 and t, I take an average, and I ask when is the trace of this object, which is the time-involved expectation value of this projector onto that subspace, when is that subspace epsilon close to 1? And this is when it's epsilon close to 1, I say it's an equilibrium. And the probability for this to happen, one can bound by this number here, or this expression. And the expression contains this epsilon here. If I allow a larger discrepancy to from 1, then this bound here will be smaller. This is intuitively correct. And the most important ingredient here is this number here, d equilibrium divided by d. So this is the dimension of the equilibrium Hilbert space divided by the overall Hilbert space. So if I can prove that for the observable chosen, the equilibrium subspace is almost as large as the overall subspace, then this number is very, very close to 1. Then this number is very, very close to 0. And then the whole expression here is very, very close, but just smaller than 1. And if it's just smaller than 1, then this shows that I almost always find my system in equilibrium. And in fact, for the macroscopic observables that I mentioned here, it can be proved that this here is exponentially in the system size close to 1, and therefore equilibration happens. So this is about the type of result that can be proved by making use of these typicality techniques, and which, if you're happy with the setting, tell you a not too special system in a probabilistic sense from that class of systems will equilibrate, shown, proven. And I think, so you have to have the mindset that you say, I don't need something shown for every single type of system separately, which would be very, very good, but I mean, there's many systems around, but I can expect any system that is not too special to do that, which is, I think, very appealing to generally get confidence in what is the mechanism, why we see equilibration so ubiquitously nature. So the claim is now that results like this explain the ubiquity of equilibration, but there's one caveat to that. It only does it if it happens sufficiently fast. So now here in this equation, there is this limit t to infinity. So it means I take here an average over a time interval, but I make this time interval longer and longer to get to the point where the system is equilibrated. But now if that equilibration takes the age of the universe to happen, then this formula hasn't explained anything, because then this is not the mechanism. We see it much earlier. We see thermalisation. My coffee gets colder much quicker than the age of the universe. So I'm saying this because once equilibration is established, I believe that I want to make the point that you also have to show that it happens on an interesting time scale, on a physically realistic time scale, so that these theorems can serve as a justification of why equilibration happens in the real world. So now I want to come to the essentially topic of the talk, which is timescales of equilibration. I will now do this, just give you a sketch what people have done before I started even working in this field, and just to give you an idea what the status is here. And I'll do this very, very superficially in some way. So we want to talk about general classes of systems. So what are general questions that we can ask that give us broader answers in this field? The equilibration time, T equilibrium, it would be interesting to have upper or lower bounds, so to say, well, we can prove that a system cannot equilibrate faster than this or slower than that. Or we can ask what is the typical time in the sense of random matrix theory, or in the sense of typicality, if you want, where this happens. And there is 3 results from the same group, Goldstein, Hara, Tazaki, that made substantial progress in the field. And the first 2 are essentially a warning. And I'll tell you in very vague words what they say. Given a system and a dimension of the Hilbert space, and you fix all the interesting parameters, and then you say, for that system, if you are allowed to choose any observables, you can always choose one such that the equilibration time is larger than the age of the universe. So if you allow for all types of observables, you can always make the equilibration time ridiculously long. And the second theorem shows that the opposite is also true. If you allow for all kinds of observables, you fix everything else, Hamiltonian and so on, you can always find an observable such that the equilibration time is almost instantaneously, like ridiculously short and not of interest in physics. We don't see everything equilibrating on a attosecond time scale or something like this. So there's a warning: we shouldn't expect all observables to do the right thing. And the next warning is that even the typical time scale doesn't do the right thing. So in a very technically very challenging work, Goldstein, Hara, Tazaki showed that for if you fix the Hamiltonian of a system and look at typical observables, then the equilibration time will be of the order of the Boltzmann time, which is way too short to be realistic. So this, for under typical conditions of room temperature, would be everything equilibrates roughly on the order of femtoseconds, which is not what we see. So a few results have been obtained. One, the last one here, in the sense of typicality, but it didn't connect to physics so well. And I think at this point, this I find very interesting, because I like the idea of typicality, but this result also tells you maybe not everything is as typical as we thought. So not all physics is typical. And the conjecture, which is also already in the paper of Goldstein, Hara, and Tazaki, is locality of Hamiltonian and observable is a crucial ingredient. they just write this one sentence. They believe that this has to be included in their analysis in order to be able to find that the typical equilibration time is on a physically realistic time scale. Now, this is now the question where, together with Daniel Nicholson, I started to work on this topic, and we thought, well, then the idea is we want to try to include locality in the questions of studying equilibration times and equilibration times of isolated quantum systems. What locality exactly means, there's different notions that can be used, but if you think of the one that you naturally have in mind, like a lattice system and only nearest or only next nearest neighbors, that's certainly in there, but we use the more general one that includes more systems, but I'll not go into this. But it has something to do with whether you can have all kinds of interactions in your system, or whether you're restricted to either only neighbors on a lattice or only to, say, pair interactions, even if they are further away. That's, I would also call local, but it's just a name. What is special about quantities being local, about a Hamiltonian and the observable being local? And now I get to what is the starting point that for the technical method that we use to address this problem. If both the Hamiltonian and the observable are local, then there exists a basis in which both are simultaneously sparse. So you look at the matrix representations of H and O, and say you, simplest case, you have a spin model, you write it down in the side basis. Then if it's a local system, then in the spaces there will be lots of zeros in there. And if you have a system that is not local, then there will be typically no zeros or very few zeros. And of course, you can go to a different basis where there's no zeros at all, but there is a special basis where both operators are simultaneously sparse. And this now can be used in a calculation to our advantage. I'll not talk about this here. I'll have this one last slide where I show you, where I think I'll give you an idea how this sparseness is used, and then I think I'll say very little or almost nothing about the actual result that we have, but I think it's more important to give you an idea how the sparseness now can be used. Okay, so what do we do in an actual calculation? Think of some Hamiltonian that you're interested in and choose a basis to represent the Schrödinger equation. And it's an unconventional choice maybe, but we chose the observable eigenbasis. So this is the states OK here. These are the eigenstates of the observable. And then I introduce these two definitions here. So these X's are the time-evolved states in this eigenbasis, and so the vector elements, and H, J, K are the Hamiltonian matrix elements in the observable eigenbasis. And using these simple definitions, the Schrödinger equation looks like this. Now this is a first order differential equation with this I in here, and which gives you something like essentially oscillators. So if I think of these X now, I mean, these X are elements of vectors of states in a certain representation. If you think of these as classical variables, then you have a set of oscillators that are coupled by these coupling strength H. Maybe it becomes even more obvious if you integrate up this Schrödinger equation to an integral equation. The classical oscillator X, which is just this quantity, has a natural frequency that is given by the diagonal element of the Hamiltonian matrix in this basis, and it's coupled with these coupling strength to all the other oscillators here, xk, that have their own frequencies. Yeah. So in this picture, these vector elements are seen as classical oscillators, and they are coupled by these matrix elements. If the matrix is, has many zeros, then many of these couplings will be zeros, and the whole thing will be a sparse network of classical oscillators. So now we have a classical mechanical problem, classical variables that are coupled, but not all with all, but only some to each other. And here I've plotted such a network, and each of these dots here is one of those variables xj. So this is like x1, x2, x3 if you want. And some of them are coupled, like shown with these lines here, and some of them are not coupled, like these two are not directly coupled. And what I've done additionally is I've ordered these nodes according to how large the eigenvalue OK that corresponds to xk differs from the equilibrium eigenvalue. These here are in the equilibrium value. These differ a little bit, these differ more, and this is the most non-equilibrium state. So now I can see equilibration in the subspace sense that I introduced before as propagation of an excitation through this lattice. If I prepare my initial state furthest from equilibrium, so everything is in that state here where my cursor is, then to reach equilibrium, this oscillation has to propagate to one of those or many of those equilibrium nodes. And propagation through a classical network, there's lots of methods and results known that one can use. So I'll essentially stop with the technical part here because my time is more or less running out, but I just want to give you the idea that realizing that networks are sparse when the observable and Hamiltonian are local gives us a tool to have a sparse network, and we can analyze classical propagation of oscillators of oscillating excitations in a classical network, and use this to calculate the time it takes from this furthest from equilibrium state to equilibrium, and in this way estimate the timescales. What we find, I have the result on the next slides. I'll not even tell you about the result. I'll just tell you we get a result that gives us a bound on the equilibration timescale, and this bound has a parameter that tells us if the system is more local, equilibration will happen slower, and if there's no locality in the system, equilibration will happen faster. So if you think of what I told you about the result of Goldstein, Hara, and Tasaki, where they found that a typical system, no locality included, equilibrates way too fast, then our result indicates if we include locality in calculation, then we can expect that the equilibration times will become slower and they will approach physically meaningful ones when locality is included. We are not there fully, we haven't shown everything that we would like to show, but this is a clear indication. We have this method here with this network, which I find very intriguing, to study a classical network and get results on quantum equilibration. And we have a result that indicates that including locality is the right direction. Okay, now I'll skip over the proper result. I'll give you the reference if you are interested enough to look it up. And we have some numerical results that nicely confirm the results, but I'll go right away to the conclusions, or here I call it take-home message. I think in the times of Corona, that's not the exact word because it's delivered like right to your home anyway, and you don't have to take it home. Okay, so maybe if you remember only one thing of the talk, I would say that typicality is extremely useful and I find very appealing approach for understanding why macroscopic systems equilibrate the way they do. And the notion of probabilistic equilibration, like in probability, not for all times, but for most times, is the right notion for isolated systems. And the third point that I haven't here, it should be equilibration on the level of observables, because not all observables can equilibrate. So I think if you have this slightly non-standard, but now like more recently established notion of typicality and equilibration, this is, I think, the most important concept that I would like you to take away from this talk. More specifically in this talk, I just outlined at the very end that we have a result that shows that equilibration times depend on the locality of the Hamiltonian and the observable. So locality is an important ingredient to find, so to have the right class of systems on observables to make then generic statements about the physics of equilibration. In terms of concepts, I showed you that a local Hamiltonian and a local observable translate into a classical sparse network in Hilbert space. And this is an interesting and novel tool to prove actual results for quantum systems that are represented by this classical network in Hilbert space. And I haven't talked at all about the tool to then, for that network, derive results, and its classical Lieb-Robinson bounds, a very useful tool in quantum and classical mechanics that limits the speed of propagation, or gives you access to bound the speed of propagation through lattice systems. And while in the very top here, I've shown that typicality is an important concept that I believe to be very useful. There's also the warning that comes with it. Not all physics is typical. Equilibration timescales without the inclusion of locality are not typical, and the locality of our physics that we observe or that we study is an important ingredient here to be considered. Open questions, there's many. I think the most interesting one is the result that I have not really shown you is a bound on the time scale. So we can say equilibration in the presence of locality will take at least that long, but it could take much longer. But the even more appealing result would probably be to calculate the typical equilibration time of a system with a local Hamiltonian and a local observable. So instead, the minimum equilibration time, it would be very appealing to have the typical equilibration time in a probabilistic sense. So finally, credit to Daniel Nicholson, who was heavily involved in this work. And I think I'll finish my talk here, and I thank you for listening and your attention. Thank you.
Yeah, Michael, thank you very much for an excellent talk, from the basic introduction to this very subtle problem to the latest stand of your research. Thank you very much. And I think we will all keep the message at home, yeah, and think about it. Ilya, would you like to guide us through the questions? I see there is one in the Q&A facility, and maybe you would like to allow people to raise their hand and pose their question personally.
Yeah, I think that we have one question from Graham, and I think we can let him talk and he can ask his question.
Yeah, will you allow him to talk, Ilya, or should I?
Can you hear me?
Ah, yeah, perfect.
Hi. I'm not sure if it's a very substantial question, but it was when you were introducing the definitions of equilibrium. I think it was during the earlier part of your talk. Yeah. The question related to the second definition, which said that for some time that the probability that the distance between the expectation value of some observable with its equilibrium value was less than some specified bound. That question just confused, or that statement confused me slightly, because I didn't understand how you could attach a notion of probability to an expectation value, since you can calculate this analytically. So I just wanted to check that, does this mean so you have some, is that for picking like you pick a value of this observable at some time t, so you're kind of picking the time randomly? Is that what the probability relates to?
you don't pick the time randomly, average over a time interval. So
okay.
let me see if I can share my screen again and show this. So this was the slide here. So what I do is okay. So what I did wrong. So there's a typo here actually. So what I wanted to do here. So there's a something like an absolute value here missing, or the size of a set. So what I really want to do, I look at all times, at the set of all times for which the expectation value does not differ from equilibrium too much. And of that set of all times, I take the probability that the deviations are not large enough. So, so maybe it's easier to think of a finite set. You take the set of times between 1 and 10, and then you look, the time evolved expectation value is close to equilibrium, and sometimes it deviates too much. And then whenever this happens, you say, okay, this little interval I have to take out. There's not equilibrium. And I do this for the whole interval. So I have the time 1 to 10, and occasionally when excursions are large, I have to take tiny intervals out, and I look at the probability for that to happen. So this is the size of the set, the line 1 to 10, taken out those little intervals where equilibrium is, where the actual value is not close enough to equilibrium, and what remains is well, it gives you a probability if in that interval you measure at one instant chosen at random. This is the probability for you to find the system in equilibrium or not.
Okay.
Did this answer your question? So
I think so, yeah.
You actually spotted a typo here. So I need something like the size of the set relative to the overall size here. But so I have to correct this in a next version of the slide. But so this is the probability of a set having the of all times in equilibrium compared to all times considered in a certain time interval.
Okay. Yeah, the only, yeah, I don't know if it's a trivial point, but the thing that slightly confused me was like the notion of probability, because if you're calculating an expectation value using some analytical formula that you showed on the previous slide, then surely it's time evolution. You can just, you know, I don't understand where the notion of probability enters in, but I can defer that for.
It enters when you say of all those times in the interval, say 1 to 10, you pick a time at random. What is the probability that at that time your time evolved expectation value deviates from equilibrium or not?
Oh, okay, right, okay, yeah. No, that makes sense, yeah.
Use a random time to make a measurement, and with very high probability, you will find a value very close to equilibrium. That is the probability here.
Okay, yeah, that makes sense, thank you.
Yeah. To find the system out of equilibrium, you either have to be very unlucky or have to pick your time very, very precisely so that otherwise probability is against you.
Yeah, okay, thanks.
Okay, I think let Ismail ask his question. Ismail, you can unmute yourself.
Hi everybody. Thank you. Can you hear me?
I can hear you. Yes.
Yeah. First of all, thank you. Fascinating talk. I love how we're able to operate at this very abstract level, and these have far-reaching philosophical implications. And yet at the same time, you made it so accessible. Thank you so much. My first question is, you talk about how typicality requires, in the definition of typicality, we restrict ourselves to some set of observables, but you allow multiple of such observables. Then later on, you talk about simultaneous sparsity between the Hamiltonian and these one observable. How do you maintain the simultaneous sparsity when you allow multiple observables?
Then there will be, all of them will be sparse on the same basis. So really think of, I think the easiest way to visualize this or to think about this is if you take a Hamiltonian of, say, something like an Ising model with nearest neighbor interactions only, then you can figure out that this means that the Hamiltonian will have lots of zeros in there, because all those matrix elements which correspond to further away like spin couplings and or three-body interactions, they are all zeros. So you have lots of zeros in the side bases. And now a first local observable would be the magnetization, like the sum over all side Pauli operators. And this will be a sparse matrix in the same basis. And now another matrix observable that is local in the sense, like meaning having only some other observable that has only pair couplings, for example, will also be sparse in that basis. So locality really means that there's huge classes of terms that you not allow, like those coupling faraway spins, or those having products of more than 2 or 3 or 4 Pauli operators in there. All those terms must be zero, and this means all those operators, you can choose 10 of them, and they will all be sparse in the same basis, because you kick out so many terms like 3-body interactions, 4-body interactions, large distance interactions, and then if they're all local in the same way, then they'll be all sparse in the same way.
Right, thank you. So I was confusing it with simultaneous diagonalizability or something like that. Okay, but thank you. You've helped me. Yeah.
No, they're not.
And then,
they're not.
Yeah, and I have a second question, if I may proceed.
Sure.
You talk about in your abstract of the talk, you mentioned quantum information results as enabling progress in this field. Which specifically, which quantum information developments were you referring to? I know you talked about propagation through classical networks, but I'm curious to know if there are other sub branches of quantum information that bring bear on this work.
Yeah. So the result from my group that I sketched briefly at the very end. So this is, as I said, this was used more by classical methods, so not quantum information methods. But I was just referring more generally that other groups, especially there's the one Bristol group around Sandu Popescu and Andreas Winter, that has contributed significantly to this line of research. And they used, for example, quantum information methods where this is the background of people like Andreas Winter, and they have, I know that Levy's lemma was an important ingredient, and others, but so the same is also by choosing which quantities to study. That you have a number of papers where the quantum information side really motivated the choice of looking at this distance measure and this type of observable to make progress in the field. And yeah, it's especially this Bristol group I was referring to. I'm not even able to tell you in great detail what those measures, what those methods further were. Yeah. Sorry, that wasn't an amazing answer, but that's the one I can give you here.
Thank you, Ilya. I have more questions, but I mean, I'd rather ask other people first.
Yeah. Okay, let me give a word to Camille.
Yeah, hello. Thank you for the talk. So yeah, my question is maybe more general. Is that I know that quantum mechanics ideally is built for unitary evolution, but if you take a quantum system or even a typical quantum system, how is realistic the assumption that this system is isolated?
Well, so this of course depends on the details, right? So first, there is the question is, of course, it is realistically isolated to some degree, which may be a very high degree or not. But the question is, how does this time scale relate to the intrinsic time scale of the system, and especially the slowest intrinsic time scale of the system, which is the equilibration time scale. Like for a system, as an isolated system, the last thing that happens is equilibration, or then not so much happens anymore, well, with some fine print. So the question is it well enough isolated such that one can reach the timescales at which equilibration happens, and then the closed system scenario that I was discussing is the one that is relevant for describing experiments. And this is something that can very well be achieved in some or even many of the cold atom platforms that people have in their labs. Of course, it doesn't mean that it's always done and can always be realized. So this is the one part where I would say, this is why these kinds of questions have seen interest on the experimental side. Then there's another section, maybe a bit more on the philosophical side, and this is by papers from that Bristol group that I've mentioned before, so Popescu, Short, and Winter. There is a pretty early paper in Nature Physics from 2006 or so, where they start from a bit of grand proposal saying, well, if we think of the whole universe, and then we assume that the whole universe, because it's everything, is in a pure state, then we can say, okay, this is now our isolated system, it's the whole universe. And then we ask, if we look only locally, what do we see? And this is again such a typicality question that can be asked. So even if the whole system is in an energy eigenstate, I can look locally. That is what we can do in an experiment. And what do we see? So then the whole universe is not studied with a density operator and a mixed state and coupled to something external. But the moment I look only locally in this isolated quantum system, I'll see results that fall into the class of results that I've shown here. So I think these are the two readings here that you say, either your isolated system is the whole universe, or it's well enough isolated such that all the interesting physics that you're studying happens before the coupling to the environment starts entering in in a relevant way.
Yeah, okay, thank you. Yeah, I was, at least the second answer, I was a bit expecting that, yeah, and if you increase enough, because yeah, there's always this thing that if your system is not isolated, you can include its environment, and if you think, oh, the environment is not isolated, you can include the larger environment, and at the end you reach like the universe. But yeah, I agree that it's a bit like philosophical, because whether or not we can consider the universe as a system evolving unitarily or not, yeah, it's a more maybe a philosophical question.
Yeah,
okay,
I agree.
Yeah, but thank you for, and so the answer is, yeah, in the lab you can build such, I mean, you can isolate your system and so see what happens. Yeah. Thank you.
okay. Next question. You can speak.
Oh, right. In cellular automata systems, and I think that the Ising system is classified as a cellular automaton. There's a kind of equilibration which is linked to locality. But my particular interest has been in those cellular automata which model fluid dynamics. It's an awful long time since I worked on those, but I think they exhibit this kind of behavior, and it depends on locality. Has a link been established at all with such simple systems that model fluid interactions?
No, not that I'm aware of. So I would say, I mean, I'm not saying that it cannot be extended in this direction, but to my knowledge, not even discrete time dynamics, and this is what you have in a cellular automata, has been studied with this view in mind. I don't see why it would be very different, but here in this setting, continuous time evolution, like under the regular Schrödinger equation, is what people have considered, and I'm not aware of anything else. So I'm afraid I don't think I can say anything more qualified to your question here.
Great, thanks.
Okay, Gary, you can ask your question.
Hi, thank you very much for a wonderful talk. I apologize if this question overlaps with what Ishmael asked earlier, but I was just wondering if you could say a little bit more about, I mean, what kinds of, a little bit more detail maybe, what kinds of observables these kinds of, or this formalism works for? Is it, would only be for, these observables that gives, the sparseness in the calculations, or these local observables, or is it a little bit more sort of nuanced than that? Thank you.
Yeah, so the sparseness I introduced only in the later part of the talk, when I was unhappy with the timescales calculated for non-sparse system. So most of the results in the field do not explicitly include the sparseness, but neither do they exclude it. So it's like, whether it's sparse or not, it's in principle all in there. So the sparseness is not the relevant point. What the choice of observable really is what I on, let me go to that slide, on this slide here roughly. And there is some technical fine print to these observables, but the main classes of observables are the three here. And I can I mean, observables, I think you have an intuitive idea what it is. To formally define it in the way like as von Neumann has done it, it is a bit of a story, but it boils down to something where you believe that this is what you really measure when you measure something in a large system. And it leads to a certain way that you can then split the Hilbert space into not a product space, but what is it? The word I'm looking for. Well, the big O plus thing.
Yeah, direct sum or something.
A direct sum, sorry, that was what I was looking for. Yeah. So, but it is what you roughly think of macroscopic observables intuitively. Subsystem equilibration is what I mentioned when I mentioned the whole universe, and you look only at a part. It's really that, and equilibration for physically realistic observables, it is something that measurement accuracy cannot be more than a certain number, like 10 relevant digits or 1,000 relevant digits, or something that is already way beyond what can really be done. So there is technical definitions here that are needed, but it is very tempting to believe that these three classes together contain essentially everything that one can really realistically measure in some way. And but they include local and non-local versions of it. And the moment you make a typicality statement, so you say something typically for picking, essentially for example, for a given Hamiltonian, picking at random one of those macroscopic observables, then you do something like a probabilistic argument for local and non-local ones at the same time.
Okay.
Which may be why some things don't work out in the right way. So certain things, the non-local ones are much more generic than the local observables. So if you make a typicality statement, everything may be overshadowed non-local ones because they are typical. And if you want to know something about the local ones, you have to work harder. It's technically more tricky, and to make a statement about only that smaller subsystem, but that is the one that is relevant. But all the equilibration proofs shown here do not consider locality at all, but are for very broad and general classes of systems where I would say, if you tell me an observable you're really interested in physically, I would have a hard time imagining one that does not fall in at least one of those three classes listed here on that slide.
Okay, okay, thank you.
Okay, then Michael, thank you very much for your talk. Sorry, I just come in diagonally. Yeah. Ilya, thank you very much for coordinating the question, but I'm just looking at the time, and we are a little bit probably time to slowly come to an end. So Michael, thank you so much for your excellent talk. And thank you to all the participants. If you have more questions for Michael, I'm sure you know how to find him, and he will be very happy to answer your questions in another setting. Absolutely. Then thank you very much, Michael. And just to announce next, probably latest tomorrow, we will send out the announcement for the next talk. So I really hope to see you again all here for next Monday's colloquium. Thank you very much. So have a good evening. Thank you. Bye, Michael. Thank you very much. Yeah, thank you.
Thanks to all of you. Bye-bye.